Bismillahirrahmanirrahim. Assalamu alaikum, dear students. In the previous lecture, we discussed about the generation of impulse in the SA node. In this lecture, we will discuss the conduction through the remainder components of the conduction system. That is conduction through the interatrial pathways, AV node, and his Purkinje system. At the end of this lecture, you will learn the conduction through interatrial pathways, AV node, and his Purkinje system. At the end of this lecture, you will also learn the consequences of abnormal conduction through AV node and bundle of his and its branches. From sinoatrial node, impulses pass radially throughout the right atrium because the ends of the SA node they are connected directly with surrounding atrial muscle fibers. Therefore, action potential originating in the SA node first passes into the atrial muscle and then eventually from SA node impulse transmission passes to the AV node. The impulse from the sinoatrial node passes through three sets of specialized muscle fibers. The first one are the anterior interatrial pathways. These are called after the name of scientist Bachman. These pathways, anterior interatrial pathways, conduct impulses to the left atrium. The middle interatrial pathways are called internodal tract of Wenckebach. While the posterior pathways are called internodal tract of thoral. These tracts consist of specialized and ordinary muscle fibers. Ordinary muscle fibers and specialized conductive muscle fibers. Some investigators assert that these pathways constitute the principal routes for the conduction of impulse to the AV node. Velocity of conduction in interatrial pathways is 0.3 meter per second, but this velocity is highest in anterior internodal pathway of Bachmann, and in anterior pathways the velocity of transmission is 1 meter per second, and it is further proposed in literature that the highest velocity in anterior pathways is because of the presence of specialized conduction fibers, just like Purkinje fibers. If we talk about the configuration of action potential in the internodal pathways, the action potential, if we compare with the ventricular muscle, the action potential in the internodal pathways shows that the plateau phase is not developed in the interatrial pathways. The repolarization occurs at a slow rate, and duration of action potential in interatrial pathways is also brief as compared to ventricular muscle. The impulses from the interatrial pathways reaches the AV node, that is atrioventricular node, and this node is located in the posterior wall of right atrium behind the tricuspid valve. The AV node it is composed of three regions. The first region is called AN region. The second region is called N region. The third region is called NH region. The characteristic features of each region are different. AN region is transitional zone. Transitional zone between atrium and AV node. The AN region is the mid portion and have slowest conduction velocity. NH region is the zone in which nodal fibers gradually merge with the bundle of His, and this portion of AV node has highest velocity as compared to AN and N regions. The impulses from SA node through internodal atrial pathways passes to atrioventricular node in 0.03 seconds with transmission velocity of 0.3 to 1 meter per second. Then there is delay of 0.09 seconds in the AV node. The cause of this delay is slow conduction in the AV node. And the reason for slow conduction in the AV node is diminished number of gap junctions. As the gap junctions are present in less number, so the impulse transmission passes slowly from AV node to the next portion, that is bundle of haze. This diminished number of gap junctions basically provide great resistance to conduction of impulse to bundle of haze. The significance of this delay is that functionally this delay between atrial excitation and ventricular excitation permits optimal ventricular filling. As this delay allows atria to empty blood into ventricles. Electrically, the conduction time through the AN and N regions of AV node largely account for delay between onset of P wave and the QRS complex of ECG. If we draw the diagram of ECG, it is composed of waves. The first is P wave, then is Q, R, S, and T wave. So, as I mentioned, electrically AN and N regions of AV node accounts for delay between onset of P wave and QRS complex. So, this is the delay about which we are talking about. The P wave represents excitation of atria as the impulse spreads from SA node to the atrial muscle. The impulse conduction through the AV node is very important clinically as there is no connection between the atria and ventricles except the AV node because atria are separated from ventricles through a fibrous band that is called annulus fibrosus, and due to the presence of this band the impulses cannot pass from the atria to the ventricles directly. So there is only one connection between the atria and ventricles for the transmission of impulses, and that connection is basically the AV node. So in the AV node, as we mentioned, that there is a delay of 0.09 seconds. After this delay, the impulses passes from AV node to this bundle of His at a velocity of 0.05 meters per second. So this is the only connection between atria and ventricles. If blockage occurs in the transmission of impulses from AV node to the bundle of His, this means that the excitation of ventricles will not occur. So, if the impulses are not transmitted from AV node to the bundle of His, or they are conducted further slowly or intermittently, then certain type of clinical abnormalities appear that we are going to discuss in this slide. The first type of clinical abnormality that occurs due to abnormal conduction through the AV node is the first degree atrioventricular block. In first degree atrioventricular block, the reason is slowing of conduction through AV node. In second degree AV blocks, the reason is intermittent intermittent conduction in which some impulses pass to ventricles while others cannot pass from AV node to ventricles. The third type of block that occurs from AV node to bundle of His is third degree atrioventricular block, that is also called complete AV block. In this type of block, impulses stops, impulses transmission stops from AV node to ventricular muscle, and due to that the ventricular excitation and then contraction cannot occur. The most common reasons of third degree atrioventricular block are some degenerative process in the AV node or ischemia of AV node. Ischemia means inadequate blood supply. The fourth type of problem is accessory atrioventricular pathways. In contrast to atrioventricular blocks, in accessory pathways, faster conduction occurs. And the reason for this faster conduction from atria to ventricles is the presence of some abnormal pathway between atria and ventricles. And this pathway basically bypasses the AV node. The example of such accessory conduction pathway is Wolff Parkinson White syndrome, in which a bypass track basically of myocardial muscle fibers exists congenitally. This is important that it exists congenitally between atria and ventricles. As we mentioned that impulses from the AV node passes through bundle of His in 0.04 seconds into two bundle branches, right bundle branch and the left bundle branch to reach the ventricles through a specialized, very fast muscle fibers that are specialized conduction fibers called Purkinje fibers to the ventricles. The bundle of his, it passes subendocardially. The bundle of his, it passes subendocardially on the right side of interventricular septum, that is the that is present between the two ventricles and separate this interventricular septum. It separates left ventricle from the right ventricle. The bundle of his, when it passes subendocardially down the right side of the interventricular septum, it divides into right bundle branch and the left bundle branch. The right bundle branch, as we can see from the left diagram, it is basically direct continuation of his bundle and proceeds down the right side. It proceeds down the right side of the interventricular septum, while the left bundle, it is thicker than the right. It arises almost perpendicularly from the bundle of his and perforates interventricular septum. On the subendocardial surface of the left side of interventricular septum, the main left bundle, it divides into it divides into thin anterior division and thick posterior division. The right bundle branch and the two branches and two divisions of the left bundle branch, ultimately they subdivide into a complex network of conducting fibers called Purkinje fibers, which further ramify over subendocardial surfaces of both ventricles to transmit impulses. Impulse conduction in the right bundle branch, the main left bundle branch, or either division of the left bundle branch may be impaired as a consequence of degenerative process or due to ischemia or coronary artery, also called coronary artery disease. The block of either the main bundle branches, that is right bundle branch, if it is the conduction through it is blocked, it is called right bundle branch block. If the conduction through the left bundle branch is blocked, main division is blocked, it is known as left bundle branch block. Block of either thin anterior division or the thick posterior division is called left anterior or left posterior hemi block. The special characteristic of the AV bundle is that the impulses normally passes only from AV node to the bundle of his, and the impulses cannot pass in the backward direction from the ventricles into the atria. This characteristic feature prevents re-entry of cardiac impulse from ventricles to atria. The reason of this inability of the AV bundle to conduct impulses in the backward direction is that everywhere except at the AV bundle, the atrial muscle is separated from the ventricular muscle by a continuous fibrous barrier called annulus fibrosus. This barrier acts as insulator. It acts as a insulator to prevent backward passage of impulses from ventricles to the atria. In rare conditions, in very rare conditions, the cardiac impulse can re-enter to atria and cause serious cardiac arrhythmias that we will discuss in detail in the next lecture. Impulses after passing from the AV node passes through bundle of His and then through right and left bundle branches to the Purkinje fibers, and through Purkinje fibers the impulses are conducted to the remainder of the ventricular muscle. The Purkinje fibers are very large fibers, even larger than the ventricular muscle. The Purkinje fibers transmit impulses or action potentials at a velocity of 1.5 to 4 meters per second, a velocity about 6 times that in the usual ventricular muscle and 150 times than in some of the avinodal fibers. This fast transmission or the fast velocity allows instantaneous transmission of impulses to the remainder ventricular muscle. The cause of rapid transmission through the Purkinje fibers is the very high level of permeability of gap junctions present at intercalated discs between successive cells that make up the Purkinje fibers. Therefore, due to this high permeability, ions flows easily. Ions flows easily from one cell to the next, thus enhancing velocity of transmission through the Purkinje fibers. The Purkinje fibers also have very few myofibrils, which means that they contract little or not at all during the course of impulse transmission. As we mentioned, the impulse generated in the SA node passes through three interatrial pathways to the AV node. Then from AV node through bundle of His passes to two branches, right and left bundle branches, and these bundle branches ramify further to give rise to very long fibers that are called Purkinje fibers, and Purkinje fibers then transmit impulses to the ventricles to cause their excitation and generate action potential in the ventricular muscle. This transmission, this propagation of cardiac impulse from SA node to AV node occurs in 0.03 seconds. Then in the AV node there is delay of 0.09 seconds that gives time to the atria to empty their blood into the ventricles. After this delay, impulses are conducted through bundle of His in 0.04 seconds. Then the cardiac impulse takes another 0.03 seconds to depolarize endocardium. Then from the endocardium, the cardiac impulse spreads to epicardium through myocardium in 0.03 seconds. Thus, we can say that the cardiac impulse takes 0.22 seconds to depolarize whole heart. When the impulse passes from endocardium to epicardium, on the left side it takes 0.03 seconds, and on right side it takes 0.02 seconds. So in approximately in 0.22 seconds, the whole heart it becomes depolarized. In the next lecture, we will discuss ectopic pacemaker, vasovagal syncope, and re-entrant phenomena that we have mentioned in this lecture also. Thank you very much, dear students, and stay safe.